And here is the agenda. For now, I'm going to minimize this so you guys can see a little bit better. So just a quick reminder, the positive physics is due tonight. Remember, it's Unit 7, which is called Systems. You're doing the work section, and you are completing the free body diagram analysis, the vocab concepts, complete problems 3, and challenge sections. You will have some time to work, probably between 20 and 30 minutes at the end of the period today. So both in class and online, you'll have that time. So if you have questions about that, I can help you out in either format, online or in person. But you'll have some time to wrap that up and get that turned in. Today, there's 2 things on the agenda to accomplish, and then the bottom 2 things are announcements more than really agenda items. But we'll be taking notes on gravitational force and electric force. And those are the last 2 topics of this force review unit. And so they are actually, though, in Unit 5B, if you go back on the topics on Axis. Everything we've been doing in the first few weeks since Christmas has been Unit 6. But these 2 topics are actually in 5B. And I'll show you that in a little bit, but that's where you'll find them. Then there is a worksheet 3, and it's assigned in the sense that I think you should do it. I'm not going to grade it. It's to prepare you for the quiz that's going to be on Thursday for A class and Friday for B class. And so it's to help you prepare. And it's also not only to help you prepare for that quiz, but also to help you prepare for the AP exam, just the different kinds of questions that they could ask. And so we'll take some time on Thursday for you guys and Friday for B Day to go over some of those questions and answer class, but I won't actually be collecting it or grading it. So you can do as much of it or as little as you wish. I'll show you here in just a few minutes what it looks like, and it has the answers on it so you can know if you're on the right track, but then we can discuss it before the quiz on Thursday, which is point number 3. The quiz on Thursday will be actually on positive physics. And so let me show you what that will include. So for those of you guys that are here, you may want to jot a couple notes down. For those of you online, you may want to take a screenshot or jot a couple notes down. But this is specifically the outline of the quiz you'll be taking on Thursday. It'll be on the Positive Physics website. The tricky part is it's over 4 different units. So it'll be a gold day. And so you guys will actually be home and the other students will be here that are coming on gold days. But you'll all just be doing it online anyway. So these are several sections that you've already had assigned to do the work section. So you shouldn't need to do a ton of review. Unit 7 is the systems part that's due tonight. So you will have seen all the possible questions because this is exactly the same assignment basically that you are supposed to turn in tonight. There are 3 questions, one of them from the free body diagram analysis skill, one of them from the complete problems 3 skill, one of them from the challenge skill. So, and it just randomly takes 1 question from each section per student, and then it randomly generates the numbers for those numbers-based questions. The next part of the quiz is from Unit 11 on positive physics, and that unit's called Universal Gravitation. And there will be 3 questions, but they're all from the same skill. They're all from the skill called Gravitational Force Problems. Then Unit 17 has 2 questions, and these you've already done before. We did these right after Christmas with Hooke's Law. And so it's the Springs and Oscillations unit. There will be 2 questions on the Hooke's Law skill. And then Unit 19 has 2 questions on electric force. So today we're going to learn about gravitational and electric force, and they really go hand in hand in so many ways. They obviously aren't the same thing, but there's a lot of similarities. Their equations look like the same thing. They just have different constants and different things you plug in, but the format is the same. You'll see as we learn it today. And so to help you practice, like I said, I'd like you to do worksheet 3 that for you guys, I can give you a handout of it. you that while you're writing things down. And on the handout, you'll see the answers are on the back. So you'll know if you're on the right track or not. And like I said, we'll spend some time in class Thursday going over any of them that you might need help with. So it'll be 10 questions. And while I'm giving you this worksheet and recommending that you use the worksheet to practice, obviously the worksheet, the wording and the style is more College Boardish. But you could obviously also go on to positive physics in Unit 11 or Unit 19 and do the work sections for gravity and electric force, and you could practice there as well. So not giving you any additional assignment, I'm just giving you this worksheet that you can use to practice with, and then telling you you can also practice with those positive physics units and the work sections there. Any questions about what to expect for the quiz? Anybody on Zoom have any questions for me? See a few people shaking their heads, so I assume we're good to go. All right, so back to the agenda briefly. Like I said, worksheet 3 is one way you can review for that quiz, and then obviously just reviewing on positive physics. On Wednesdays, so this Wednesday is an A day, next Wednesday is a B day, and it alternates. So what that does is, and because they're short periods, they're only 45-minute. So because they're shortened and they alternate, it throws off the schedule for testing and quizzing. So we're going to use those Wednesdays as AP exam review days. So I'm going to bring free response questions or assignments from the AP Classroom website or things like that. And we'll be doing those kinds of things on Wednesdays. Since we're, just a couple of months away from the exam now, we're going to start focusing those Wednesday times on any kind of AP exam review. I might give you practice multiple choice questions to go through, might give you free response questions. We might work in groups here in the classroom and breakout rooms online, but we'll be focusing on just preparing more generally for the exam, not necessarily even material we're covering right now in our current material. It might be things from last semester, but just helping you prep for the exam. So that's how we'll use our Wednesday shortened periods. So for this week, for A day, obviously today we're going to take our notes on gravitational electric force and then give you time to either finish the positive physics assignment that's due tonight or practice gravitational electric force problems from the worksheet or from the positive physics site. And then on Wednesday, we'll do AP exam review. And then on Thursday, you'll take the quiz. And there will be some work for you to start on circular motion, which will be the main topic for next week. For B days, because some of you watching the video will be in a B day class, tomorrow you'll be taking the notes, or Tuesday, you'll be taking the notes on gravity and electric forces. And then you won't meet Wednesday. And so your AP exam review will be next Wednesday, a week from this week, or a week from this coming Wednesday. But you'll take the quiz on Friday. So nothing we do on Wednesday will be directly related to preparing you for the quiz. The Wednesday will specifically be bigger picture exam prep. All right, everybody understand the schedule? Any questions about that at all? Yeah, Johnny.
What unit is worksheet 3 under on Axis?
5B. I'm actually getting ready to go to the browser and show you a couple of things, but good question. Any other questions? All right, so let me go to the browser and just make sure you're not only hearing these things, but seeing everything I'm talking about so that it's hopefully abundantly clear. All right, so we go to the browser. This is the teacher version. I was working with a student on a question last period. So let me log in as my fake student here. So in terms of taking the quiz on Thursday for you guys and preparing for it, it should take you to Unit 7 right now because that's the one that's due tonight. If you click on the assessment, you'll see it's locked, but you'll also be able to see there's one question from this section, one question from this section, one question. So you can review the work you've just completed for the assignment to make sure you're prepared for that. Then if you go to Unit 11, Universal Gravitation, we haven't done any assignments here, but if you click, you can see it's all, the work section's all unlocked. If you go to the assessment, you can see the quiz will have 3 from just this line. Okay, so you can come back here. There's a video. You can practice this as much as you want. All right, and then the next one is 17. If you click on the assessment here, you can see it's just 2 questions about Hooke's law. And so you've already been assigned those earlier this semester, so, but you could go back and watch the video and review if you want. And then 19 on electric force, if you click on the assessment, you can see there's just 2 questions from this electric force unit. And so you can come back here, practice these problems, and it's all unlocked so you can prepare. So you can use the positive physics work section to prepare, and you know exactly how many are coming from every portion, 10 questions total. It'll be a little bit more annoying to submit it on Axis because you're going to have to take 4 screenshots because it's 4 different units, but they're actually working on making it so you can build your own quizzes and such, but they haven't developed that yet. So for now, you'll just have to take a screenshot of each of the 4. Okay. Questions about the positive physics quiz or how to prepare for it? All right, so let's go to, well, I'm gonna have to log back in. So while that's logging in, let me show you the worksheet 3, what it looks like. You can see at the top, it says Unit 5, Quantitative Force Models. And this has a bunch of different kinds of questions. We're gonna learn what the equations are that would help you solve them for. It starts mostly with gravitational questions at the top, and then it switches more to electric at the bottom. There are fewer electric questions because they just, over Christmas break, as I mentioned, they told us they're not going to have anything over the electricity unit. But they didn't specify whether you still need to know electric force. You definitely don't need to know circuits or Ohm's law or anything like that. But you may still need to know the electric force. And so, because it's often taught in the force unit. So I'm going to go ahead and still teach it to you. And I gave you a couple questions here to practice. All the answers are on the second page, so you can see if you're on the right track. I forgot to double check and see if they all have the correct sig figs, but at least you'll know numerically if you're on the right track. So that's what that worksheet looks like. Keep getting signed out here. And the place that you would find that worksheet once you go to Axis, you guys are seeing Axis trying to open right now, aren't you? Online. You guys seeing Axis now online on the Zoom? Okay, good. So you'll go to Topics, and you'll go to Unit 5B. So most of the things we've been going over have been in Unit 6, but gravity and electric forces are actually in 5B. So if you click on this, you can see there's a lot of things we've already covered, like friction and springs and stuff. But here's the notes on gravity. Here's the notes on electric force. There's a separate gravity worksheet if you just want more practice, and a separate electric worksheet if you want more practice. Here is worksheet 3, though. That's the one that I gave you guys a printed version of, because it's got both mixed together. All right. Any questions? We good to go? All right, so a fair bit of announcements and reminders and stuff. I forgot to put the quiz on Axis, so I'll do that during my lunch break today and get that uploaded for you. And I will put this information in the description. So if you didn't get it jotted down today, well, this video will be posted later today too, but you could either go to the video or you can look in the description of the quiz and it'll be there. All right, well, let's get into the notes then. So gravitational force. Gravitational force is something we've talked about to some degree, because we've already learned how to calculate weight. How do we calculate someone's weight? We sometimes call it gravitational force or weight, but how do we calculate it? And you guys online can also unmute and speak up.
It's the person's mass times the force of gravity.
Not the force
Or
of,
yeah, the acceleration due to gravity.
excellent, excellent, yeah. So we take the person's mass times the acceleration due to gravity, and that tells us the weight. But that's a very specific application of gravity. We're only talking about something's weight on Earth, right? Or we have to figure out what that acceleration value would be for other places. Well, gravitational force, more generally speaking, in this case it's called the universal law of gravitation, is universal. It's not just weight only, it's much more broad than that. So as we go through these notes, here's my recommendation. Number one, don't write down everything you see on the slides. The slides are more geared towards helping you recognize, almost like a textbook, helping you recognize some images and some brief thoughts. We'll have you both online and in the room taking turns reading some of them. I'll read some of them. It's more just to kind of have a dialogue and create some conversation about it. So it is known that Earth is a sphere and objects that are near the surface tend to fall down. Here we've got a picture of some skydivers. So there's no reason to put that in your notes. I'm just trying to highlight the function of these is more discussion based. I'll try to emphasize the things you really want to make sure you write down, but you won't be able to keep up if you try to write everything you see. So, all right, Newton's law of universal gravitation. So Newton connected ideas, and the legend goes that an apple fell and hit him on the head, and he's like, Eureka, or whatever, I figured out gravity. Gravity pulls things down, whatever. Who knows if that legend is true, but he did connect the idea that things that fall, like an apple falling out of a tree, relate to things in orbit, like the moon going around the Earth and the Earth going around the sun. And his concept, we talked about this before when we first started learning about gravity, was that if he could stand on top of a mountain, if you remember that illustration we talked about, stand on top of a mountain and shoot a cannon, if he could shoot it fast enough, the curve of its parabolic path would start to match the curve of the Earth, and it would never hit the Earth, right? And so his idea was, well, the moon is being attracted to the Earth. There is a direct gravity pulling the moon down to the center of the Earth, but it stays in its orbit because it also has this velocity to the side. And so while it is being constantly pulled to the center, it has a velocity going sideways, which creates this constantly changing path that ends up keeping it in orbit. Now, if the moon somehow suddenly gained velocity, it wouldn't stay in its current orbit. It would actually end up going at a different distance from the Earth. If it lost velocity, it wouldn't change, it wouldn't keep its same orbit. So if we think about satellites like the International Space Station, those have a very specific velocity that keeps them at their very specific location. If they speed up or slow down, they will not stay in their same orbit. They will go into a different orbit. Okay, so we're going to learn how do astronauts figure that out. How do they know how fast it needs to be going? And it's a integration of kinematics with this universal law of gravitation. All right, can I get one of you three in the room to read this one for me?
Sure. Newton's third law tells us that the force on each mass is equal. That means that if I drop a pen, the force on Earth pulling the pen down is equal to the force of the pen pulling Earth up. However, since the mass of the Earth is so much larger, that force causes the pen to accelerate down while the movement of the Earth up is completely unmeasurable.
So we've talked about this before, that Newton's third law sometimes feels weird to think about. It feels illogical, but in reality, if we stop and recognize that it's just another application of Newton's second law, that it's just force equals force, or ma equals ma. If their masses are very different, their accelerations are going to be different, right? Because ma equals ma. So if we use Newton's second law to sort of help understand Newton's third law, sometimes that mathematically makes sense. So the pen has a very small mass, a very, very small m, and the Earth has a huge mass, so a very huge m. Therefore, the pen's acceleration will be huge, and the Earth's will be minuscule. And so that's the idea here, just a reminder of that concept. All right, now Newton concluded, as he did lots of research, he and others, that objects attract one another with this gravitational force, as it became to be called. The magnitude of that force decreases as the centers of the objects get farther apart. So if you look at these two pictures, I would say in some way you may want to jot something down about this in your notes, that the farther they are apart, the weaker the attraction. Probably pretty logical, but good to have written down, or at least committed to memory, that the farther they are apart, the weaker the attraction. And that the attraction is based on how far apart their centers are, not the surfaces. Now, as Newton studied this more mathematically, he found out that it was not a linear relationship. It wasn't just a straight up inverse relationship, or inversely proportional. There was more to it than that. So not only was it not linear because it was inverse, it was also not linear. If all you did was took the inverse and tried to linearize it, it still wasn't linear. So there was more to it than that. And what they eventually discovered through data and other research is that it is what we call an inverse square proportion. So mathematically, the magnitude of the gravitational force decreases with the inverse of the square. In fact, let me go ahead and highlight that phrase. And inverse square rules, inverse square relationships are relatively common in science. If you've taken chemistry and you've learned about nuclear radiation, there is an inverse square relationship in terms of radiation exposure. We won't be covering waves and sound anymore because of the change in curriculum. But in sound, there's an inverse square relationship in how loud the sound is. The farther you get, it's not just a linear relationship, or not a straight up inverse relationship. And then when we talk about electric force later today, same thing. So it's not just a straight inverse connection, it's an inverse square. So if I double the radius, if I double the distance, it doesn't just cut the force in half, it cuts it in 1/4. Okay. If I triple the distance, it doesn't just cut the force by 1/3, it cuts it by 1/9. Okay. So it's an important thing to remember. And this equation that you can see here, and here F1 equals F2, they're just trying to show the Newton's third law, that the forces they're feeling on each other are equal, but this is how we find the magnitude. Now, the magnitude is going to be measured in newtons, just like every other force. And so our G value is a constant. It's called Cavendish's constant, or the universal gravitation constant. And it's not something you'll have to memorize. In fact, this equation isn't something you'll have to memorize. You guys can't see what's on this paper. Even you in the room can't really see from where you're at what's on the paper. But this is the AP formula list. And hopefully you guys have a copy somewhere of your own. And on the side that's mostly full, right under the list of variables, it's like the 4th or 5th one down under that list is this equation. So you don't have to memorize it, but you need to know how to use it. And then on the other side, that's got the big blank spot on the bottom, and this box up at the top, there's a bunch of constants. And the universal gravitation constant is right here. So it's something they're going to provide for you, both the value of that G and also the equation itself. All right, let's continue. The force that these objects feel is in a straight line, and it is a straight line from the center of one object to the center of another. So on this slide, they're again just trying to emphasize that it is a Newton's third law example. And so these little subscripts, this 12 is actually the force of object 1 on object 2, and this 21 means actually the force of object 2 on object 1. It's just trying to show that they would be equal and opposite. The force that this one exerts on that one is equal and opposite to the force this one exerts on that one. So just a visual reminder that Newton's third law applies to every force pair, including gravity. Okay. Now the G value is this number. You may want to jot this number down in your notes. I mean, like I said, you can always look it up. It's on here. You're never going to have to memorize it, but it is kind of handy. And one other reason that you may want to jot it down is the way that it is written on the AP handout is with units meters cubed per kilogram second squared, which works, but it's messy to figure out how the units cancel. If you use the units as Newton meters squared per kilogram squared, the units line up very nicely. They are equivalent. We could prove it algebraically. We could draw them on the board and prove that they mean the same thing. I'm not going to take the time to do that, but the units you see on the handout are slightly different in their organization, but they are equivalent. I happen to like to write it the way it is on the screen. Now, that value was actually discovered by Henry Cavendish many years later, but he actually, it's kind of interesting how he figured it out. He had these huge metal spheres. He put one of them fixed to the floor that wouldn't move. And then he had two other ones hanging on a beam from the ceiling. And it was on a pivot point, so it could spin. And it just could rotate. And his idea was, well, if this one's fixed on the floor, and these are like several 100-pound spheres, like really massive. He said, well, they have enough mass, they should generate a gravitational force. And so if I have these two up here just hanging on a balance beam in the air that can rotate, and the only thing slowing them would be the air resistance, which would be pretty minimal, the two spheres should attract to each other and move. The ones that can move should move towards the one that's fixed. And he actually was able to measure how rapidly it moved, how long it took, and then from the kinematics, figure out the acceleration. From the acceleration, figure out the force, and from the force, generate a value for this constant. And so this constant was experimentally determined. It has been performed over and over again in lots of different ways to prove it. But even in the late 1700s, they were able to determine this constant for that equation. So kind of interesting background story there. Now, when we use this equation, it's this first one we could do as mental math, but most of the time you're going to want to have a calculator handy. So hopefully you guys brought yours. Hopefully you guys at home have yours handy. We'll talk this one through. What is the magnitude of the gravitational force between two 1 kilogram objects which are located 1 meter apart? So we've got our equation down here. We've got our G times m1 m2 over r squared. So the G is this 6.67 times 10 to the negative 11. M1 would be 1 kilogram. M2 would be 1 kilogram because they're both the same. R would be 1 meter squared. So we've got this number times 1 divided by 1 squared. So this one we can't actually do in our head. The answer is just this 6.7, right? Because it's all ones. But just helping you kind of visualize the application. We won't take a ton of time on this because it is just straight up algebra. There's nothing too surprising. You just plug the numbers in. This one, what is the magnitude of the force acting on a 4 kilogram object, which is 1 meter from a 1 kilogram object? So we're going to take this constant for G. M1 would be 4 kilograms. M2 would be 1 kilogram. R would be 1 meter squared, which is still just 1. So 4 divided by 1, 4 times 1 divided by 1 is just 4. So the answer is going to be 4 times this. Now, this is almost 7. What's 4 times 7?
28.
28. So just knowing that, which of these answers can you assume is probably the right answer?
2.7.
Yeah, this is a little less than 7, so it should be a little less than 28, right? Notice that this went to negative 10. So it's up by a power of 10, right? So that's like 27 times 10 to the negative 11. So this is the kind of thing you can do when you're doing a multiple choice question on the exam, is without even using your calculator, seeing the mathematical relationships and sort of shortcutting it, or you can just plug them all in and find it. But you can kind of see this one. If you make those connections, you can sort of predict, oh, it's got to be C. But you can also just plug all the numbers in and prove that it's C. All right, what is the magnitude? Let's skip that one. It's just the same thing. You're just going to be plugging the numbers in. But I want to have you practice one problem. So let's have you practice this one. Because I want to have you practice using the whole times 10 to a power on your calculators. So what is the magnitude of the gravitational force between the Earth and its moon? Well, the distance between them is 3.8 times 10 to the 8th meters. The mass of the Earth is 6 times 10 to the 24th kilograms. The mass of the moon is 7.3 times 10 to the 22nd kilograms. And here is the value for G. So go ahead and work on solving this. I want to make sure you can all figure it out on using your calculators and discover whether you need help with that or not. And when you get the answer, go ahead and put it in the chat. If you need to borrow a calculator, for you guys that are here, I have 10 of them back there and a charger on that back table. You're welcome to grab one. For those of you at home, once you get an answer, just type in the letter of your answer in the chat. All right, we're getting quite a few people online, all agreeing on C is the option. Are you guys coming up with the same result here?
Yep.
Okay. A couple comments just about the calculator. If you, and it depends on the calculator, but down by the alphabet buttons, there's an EE button right beside the A. And if you use that EE, anytime you've got a times 10 to a power, so to put in 3.8 times 10 to the 8, I would type 3.8 EE8. And that ties all of that together as a single number in the calculator's understanding. If you do 3.8 and then literally times 10 raised to the power of 8, and then you have other numbers with those same times 10 to the powers and you're multiplying some and dividing by some, if you don't use parentheses, it gets pretty confused about what the times 10 is supposed to go to sometimes. it very strictly follows an order of operations that may give you the wrong answer. So using that EE button is quite helpful. If you're having trouble getting the answer, when we have work time later, I can open up the TI Inspire app and help you. I doubt if very many of you need that help, but if you do, by all means ask, because I'm more than happy to kind of walk you through how to do that in case you're not too familiar with that on the TI Inspire. All right, another kind of question that we won't go through this one, but you could find, for instance, the gravitational force between the Earth and the sun, just doing the same formula. You could find this is something I would do sometimes when we were all in class and didn't have to social distance. I would have them figure out what the gravitational force between them and another student in class was. And so they would have to be willing to say what their weights were, but then they could actually, or their masses, and then they could actually find out the gravitational force between them. This one is interesting. What is the magnitude of the gravitational force between the Earth and you? And you're welcome to try this if you'd like. We're not going to take the time now, but if you put this in for G, put in your mass, put in the Earth's mass, put in the Earth's radius, you should get your weight in newtons, the same as if you took your mass times 9.8. Okay, it should give you the same value. So if you're curious to see that, it might be slightly different, like you might get, one off or a decimal point off or something, but that is another way you could find your weight. Obviously, taking mass times 9.8 is much easier than using this, but you should be able to find it either way. Okay. All right, the next part that you need to understand about gravitation is called gravitational field. So this is something that often comes up in multiple choice questions. And in fact, the previous topic, usually multiple choice questions, very seldom is there a lot on gravitation in the free response. So just be aware of that, but very frequently you'll see gravitation concepts in the multiple choice. So if it's a gravitational field question, here is the thinking behind it, or the rationale behind it. While the force between objects can always be computed using the formula for Fg, it's sometimes convenient to consider one mass as creating a gravitational field and the other mass responding to that field. That's what we're talking about when we think about the G, the 9.8 acceleration due to gravity. We're saying the Earth is massive. We're focusing on our relationship to the field of gravity that the Earth's creating. Now, the way that you can calculate that 9.8 is by using this universal equation. And that's what they're walking you through here. Here's the base equation. And here they're just saying, well, let's just pull out, using the associative property, let's put this in parentheses and pull that out. That those two statements are equivalent. We've just associated gm1 over r squared. And then they've changed the variables a bit. They've used capital M for the planet, whatever the bigger object is, and then small m for whatever the smaller object is. And they said, well, we also know that you can find this gravitational force that we call weight by m times g. And on Earth, g is 9.8, but g could be any value. Depends on where you're at. If you're on the moon or if you're on some other planet, it would be different. Or even if you are in a space station off of the surface of the Earth, the g value would be different. So whatever that g value is times the mass gives you the weight wherever you are. So if we know f of g is capital G, capital M over r squared times little m, and it is also little mg, we can set those equal to each other, and what cancels?
Masses.
Yeah, the lowercase mass, the m here and the m there would cancel. And so little g for acceleration due to gravity is equal to capital G, Cavendish constant, times big M, the mass of whatever the planet is or whatever we're talking about, divided by the distance between them squared. So this equation is also important in a way that you can find the value for G on any planet, which could be a question that they could ask. Or they will sometimes ask questions about proportionality. So if the Earth's mass doubled, this big M here, if this doubled, What would that do to the acceleration due to gravity? Someone from the Zoom, unmute and tell us. If we double the m, this big M here, what will that do to the value for g?
Double it. Acceleration will double.
Double it. It'll double. Good. If we double the distance between them, so someone on Zoom but not Ethan, since he just answered the last one, if we double this r value, what does that do to the g, the little g?
It would shrink it
By how much?
half.
Close. Since it's squared, it wouldn't be just half.
Square root?
What's,
Oh, double.
if this is 2, if we double this, 2 squared is 4. So the value of g doesn't get divided by 2, it gets divided by
4.
4. Yeah, so if we double this, that means g would be 1/4. The acceleration would be 1/4. You guys following okay with the proportional thinking? That's another kind of question you would potentially see on the AP exam. All right, I think that's good for there. Let's jump down to surface gravity. And this is another concept that they might ask you about, a different way to think through a different kind of problem. Someone in the Zoom, could I get you to read this slide for us?
Sure, I'll do it.
Johnny?
Planets, stars, moons all have a gravitational field since they all have mass. That field is largest at the object's surface, where the distance from the center of the object is the smallest, when r is the radius of the object. By the way, only the mass of the planet that's closer to the center of the planet than you are contributes to its gravitational field. So the field actually gets smaller if you tunnel down below the surface.
All right, so even though when you tunnel below the surface, you are decreasing the radius, if you think about how much mass there would be above you, even with a small decrease in radius, because all the crust of the earth that's further than you would not be pulling you in anymore. So you would dig down and decrease the radius, but then you would have this huge change in the amount of mass that's no longer between you and the center of the earth. So just an interesting concept there. Not really something you probably tested over, but something to think about. So here is the kind of question that you could be asked. Determine the surface gravity of Earth. Its mass is given this, the radius is this. So we just plug it into the equation and we can see based on these bits of information, G would be pretty close to 9.8, like we expect it would be. So that's a way you could apply this equation. If you were asked to find the surface gravity or the acceleration due to gravity on the sun, if you knew the mass of the sun and the radius of the sun and the value for g, we can find out the acceleration due to gravity for the sun would be 272, so much, much larger than the Earth's 9.8. All right, and you could find that for any question. These are the kinds of questions here, like I asked you a minute ago. What if you double the mass of the Earth? What if you triple the mass of the Earth? What if you double the radius? All those kinds of things. So those proportional thinking questions are common. All right, gravitational field in space. So here we're going to wrap up our last bit on gravity today. And this is the last sort of thing to connect when you are asked questions about gravity. What if you're talking about a space station or something that's in orbit, not on the surface of the planet or the surface of the moon? Someone in class, can I get you to read this slide for us?
Should I go again? Oh, while gravity gets weaker as you get farther from the planet, it never becomes zero. There's always some gravitational field present due to every planet, star, and moon in the universe.
So we're not just being pulled in by the Earth. We're being attracted actually gravitationally by all kinds of planets and suns and stars. But the only one we really feel because of the great distance between us and other things is the Earth. All right, someone in the Zoom, read this one for us.
I can.
Thank you.
The local gravitational field is usually dominated by nearby masses since gravity gets weaker as the increased square of the distance. The contribution of a planet to the local gravitational field can be calculated using the same equation we've been using. You just have to be careful about R.
All right. So in problems like space station kind of problems, you have to be careful. And then here we're going to illustrate that here in the next couple slides. Someone else in the Zoom, want to read this one for us?
Sure. The International Space Station is a research facility, the on-orbit construction of which began in 1998. The space station is in a low Earth orbit and can be seen from Earth with the naked eye. It orbits at an altitude of approximately 350 kilometers above the surface of the Earth and travels at an average speed of 27,700 kilometers per hour. This means the astronauts see 15 sunrises every day.
So given that information, we could figure out what is the value for G for those astronauts on the Earth, because the Earth is the largest mass close to them. And so the Earth is what's going to be creating the largest gravity, but they're not just at the radius of the Earth in terms of the distance. So it's going to be less than 9.8 because the radius is increasing. When you divide by a number that's bigger, you get a smaller value, right? So if we think about this, this is how you'd have to change that question. If we know that the space station is this far from the surface of the Earth, this is not to scale, obviously, then we would need to figure out, okay, what is this total distance r here, lowercase r? It would be the radius of the Earth plus this additional height above the surface. So if you're ever asked a question about something that's orbiting in like a satellite or a space station above the surface of a planet, you need to make sure you don't forget to include the height it is above the surface from the actual radius. And they will usually give those values as two different numbers. They don't typically say, oh, the centers are this far apart. They'll generally say the radius of the planet is this, and the satellite is orbiting this high above the planet. So you just have to make sure you recognize you have to add those two distances together to get the entire distance between their centers. All right, and that is all we have for gravity. Any questions from the crew? Anything you want to ask about gravitational force? No? All right. We're going to just take a few minutes then to talk about electric force. It'll be much shorter because basically I don't know how much you're going to be, I don't think you're going to be asked to know very much anyway, maybe nothing. So I don't want to spend a ton of time on it when it could be not on the exam at all. But I do want you to at least have some connection so that if you take AP Physics 2, you've heard a little bit about it. And if it does show up, you'll at least know how to use this equation. But in the 18th century, so also in the 1700s, other scientists, Joseph Priestley and John Robeson and others, were trying to understand how electric force related. And they had been studying gravitational force, but then they also started studying things like electric force. And they came up with this mathematical reflection on gravity that and electricity that is an inverse square rule. Okay, just like we saw it was an inverse square rule for gravity, it is an inverse square rule for electric. And when we talk about electric, we're really talking about electromagnetism. I'll come back to that. So just throw out that term for now, electromagnetism. All right, so you don't have to know about the history. They never asked you about, on the AP exam, they never ask you about dates. They don't ask you about people. But I think sometimes, especially if you like history, it helps you kind of tie in, when was this happening? Who were some of these people that were trying to figure all this stuff out? The main thing here is that just like gravity, electricity is an inverse square relationship. So the distance between the particles, as it increases, the force that they feel decreases. All right. Charles Coulomb was another one who also published a paper. His paper included information from Priestley and Robeson, and they were actually able to determine based on similar experiments to what Cavendish did with that torsion balance for gravity. Instead of using massive metal beams or spheres on beams, they were using much smaller things because, as we'll come to find out, electric force is many, many times greater than gravity. And so they didn't need to use massive objects. They could use small objects, but they used a lot of the similar kind of principles and came up with this relationship. So this is Coulomb's law and the equation you need to know. Again, it is on the AP formula list. It's on the side that's mostly full. It's in the very top right-hand corner. But I'll give you a few seconds to write it down and maybe glance over what each of these variables means, and then we'll talk about it.
Mr. Webb,
Yes.
I'm not sure if it's just me, but I can't see the new slides that you're sharing.
Oh, okay. Let me, I'll bet it because it's a different smart notebook, it's not showing it. Now can you see it?
Yeah.
Yes.
Sorry about that. I can quickly show you the two slides. I won't talk over them again, but here is the first slide we looked at. So this is Joseph Priestley. This is John Robeson. And this is just showing that the electric force is proportional to an inverse square kind of relationship. So that was the first slide we looked at. The second one was about Charles Coulomb, so you can get a vision of what he looked like. And just same relative time frame. He was working with Priestley and Robeson and also simulating Henry Cavendish's torsion balance research, but with electricity. And this is the most important part, the equation that they were able to develop with their experimentation. And hopefully as you look at the format of this equation, you see that its style or arrangement is identical to the gravitational. We have some kind of a constant. In gravity, it was capital G. In electricity, it's a small k. And again, not something you'll have to memorize. They give it to you right here. In fact, they're right one above the other. K is here and G is right underneath. So on the AP formula list, they give you that value for K, just like they give you for the value for G in gravity. Q1 is, Q is the variable for charge. And so Q1 would be the charge that the first object has, and Q2 would be the charge that the second object has. And you'll notice that they have absolute values. The reason that they have absolute values is we don't really care if they're positively or negatively charged if all we're trying to find is the magnitude of the force. The positives and negatives tell us whether they would be repelling or whether they would be attracting. And we'll discuss that here in a minute. And then the R is the same as it was in the gravity equation. It is the distance between their centers. The distance between their charge centers, though, instead of their mass centers. And most often we're talking about small objects. We're usually talking about electrons and protons and things like that. So generally speaking, the center of them is relatively, they don't necessarily always emphasize that it's from the center of one to the center of the other, but you can assume that because they're such tiny particles. All right, and you can see down here at the bottom, it just says, note the mathematical similarity to Newton's law of universal gravitation. They have the same pattern. And just a couple slides to wrap up. We'll just kind of read them through here. I'll read this one. Coulomb's law is used to calculate the magnitude of the force. Each object exerts the same force on the other, except in opposite directions. Newton's third law applies to all forces, not just mechanical ones. Since electric force, like all forces, is a vector, you need to specify the direction of the force whose magnitude was determined by Coulomb's law. This is done by looking at the signs of both charges. Remember, like charges repel and opposite charges attract. So you may have learned this in another science class. If you've taken chemistry, you for sure learned it. You hopefully, if you've had chemistry, you know all matter is made of atoms, and all atoms are made of protons, electrons, and neutrons. And protons are positive, electrons are negative. If they have the same charge, like positive and positive, they will repel each other. If they have opposite charges, they will attract. So when we look at the signs just tell us, oh, they have the same sign. So this is the force of them pushing against each other, repelling. If they have opposite signs, say, oh, this is the force of them attracting each other. Kyle or Kate, would one of you be willing to read this one for us?
Yeah, I'll go.
Okay.
Both forces are expressed using a similar mathematical formula where the magnitude of the force decreases as 1 over r squared. Electric force can be attractive or repulsive, like charges repel, opposite charges attract. Gravitational force is always attractive. Electric force is on the order of 10 to the 36th power times stronger than the gravitational force.
All right, so the last statement there about how they're different is just a trivial point, but kind of interesting how much stronger electric force is than gravity. In our life, we feel like gravity is so strong, it holds us to the earth, it's hard to escape. And yet electric force is thousands of times, millions of times larger than the gravitational force. And then as you heard, gravity always attracts things. There's no such thing as a repulsive force for gravity, but electric force can be either one, depends on the charges. All right, someone on Zoom, read this one for us.
I'll read it.
Thanks, Matt.
Dynamics covered the contact forces, normal, tension, and friction. Newton's third law applied to them, as it also applies to electrical forces. Is there some deeper connection between the electric and the contact forces? Hint, what are cars, baseballs, water, and people made of?
Someone on Zoom again, want to read this one for us? All right, I'll do it. Large macro objects are made up of atoms. Atoms are composed of a positive nucleus surrounded by a cloud of negative electrons. The predominant force acting between atoms is the electric force. At the macro level, the predominant force is still the electric force. Since there are so many atoms involved at this level, it's easier to describe these interactions in terms of non-fundamental forces, such as normal force, tension force, and friction. And last one, someone in here want to read this one for us?
The normal tension and friction forces are called contact forces as they involve objects touching each other. Gravitational and electric forces are non-contact forces. The cause of these contact forces is the electric force.
So it's interesting that it's the electrical force, those attractions and repulsions, that actually create friction and normal forces and tension forces. If there was no attraction between the atoms to hold them together, tension couldn't exist. If there was no repulsion forces between protons of one and protons of another, normal force couldn't exist. So electric force is more fundamental, just like gravity is more fundamental. Normal force, tension force, friction forces, they have their own equations, some of them, like friction force does, but they're not fundamental forces. They rely on the fundamental forces of gravity and electric. And that is it. So we've covered everything you need to know about gravity and electric. Pretty heavy section of notes, more than we normally do, but just wanted to try to wrap it all up today. And so we would be ready for that quiz. And we really need to get going into circular motion and rotational movement next week. So got to make sure we don't fall behind schedule at all. All right, if you have any questions for me about today's lesson, if you have any questions for me about the positive physics assignment that's due tonight, if you have any questions about The quiz coming up on Thursday for you guys, Friday for B-Day. If you have any questions about anything, you can stick around and I will keep the Zoom running until 11:25, so another 20 minutes or so. Otherwise, you can be dismissed, and I'll see you on Wednesday. Remember, Wednesday we'll be focusing on prepping for the overall AP exam. So good to see you guys online and in class. You guys are obviously stuck here for a few more minutes, but on Zoom, you're welcome to be dismissed unless you have questions for me.